Hello everyone. In this lecture, we are going to discuss about the cache memory management. In cache memory management, there are three schemes we are going to discuss. First is direct map, then fully associative and set associative cache. So let's understand the functioning of cache memory. In operating system, we have already studied that we have main memory. We divide the main memory into equal size frames and we divide our program into equal size pages and we load our pages inside the main memory, right? And frame size we consider as equal to the page size, right? You do understand this scheme, I guess. So let me brief you on that. Let's say we are having RAM. Let me in the color. We are having RAM like this. And inside the RAM, we create a number of frames. And let's say there is a program or different processes. And there may be more than one process. They may have variable size also. So these are two different processes or programs. And this is your main memory. I'm writing in short MM. This main memory we are dividing into equal size frames. So each and every frame is having equal size that we are having here. Let's try to understand. Okay. And now, so these divisions we consider, these are frames. These are frames. Similar size divisions we create for the process. Let's say we are having divisions like this. There are multiple processes, we can have the same size division for all the processes, those we want to load inside the main memory, like this. So here we are creating pages, and each pages we consider frame size and page size are equal. So we know that frame size is equal to page size, right? So there's not a problem. Pages we can start loading inside the main memory in a non-contiguous manner. Wherever the frame is available inside the memory, the pages can be. Now let's talk about the cache management, how the data will be shifted from main memory to cache memory. That is the point of discussion for this lecture. So if you understand this paging scheme, you can easily understand the cache memory management. So let's discuss the cache memory management. So I'm just taking the same background of main memory. So let's say I'm taking this thing. This is our main memory, and this main memory is available here. Let's say now main memory you are dividing into number of blocks here. Here we are saying this is block. These are blocks. Block will contain some number of words. So what is the word length? Word length is the block of data lesser than the size of block. The address cannot be generated for that. So let's say if your word length is 4 byte, that means the addresses will be associated to each 4 byte. So if you want to address any 2 byte in such a memory which is having block size or word size as 4, we will not be able to get 2 bytes. Right. So this is the minimal addressable length. Word length means minimal addressable data unit. Right. So let's assume that the word length is generally 1 byte. I'm assuming in terms of RAM because RAM is byte addressable. So word length, if you assume 1 byte, that means for each and every byte, the addresses can be generated. Right. So this is about main memory. Main memory means a RAM. And let's assume you are having cache memory. So let's say if you are having cache memory, this is cache memory. And these equal size division of cache memory we consider lines. So these all are lines. Cache memory is being divided into lines, different lines. And main memory is being divided into number of blocks. And block size is equal to line size. So the data from the main memory will be shifted to the cache memory block by block. And because size of line is equal to the size of block, one block can be directly loaded to one line, right? Now first let's discuss the direct map cache memory management. So let's take a scenario. Let's say your cache memory size, let's say if you are having, so I'm assuming cache memory size is 16 byte. Okay, and let's say I'm considering the block size is equal to 4 byte. And the physical memory size or main memory size, let's assume, let's say 64 byte. Okay, and word length is 1 byte. That means each and every byte is addressable. So that means when we divide this main memory into number of blocks, how many blocks? So number of blocks, if you calculate number of blocks in main memory will be main memory size divided by block size, right? So in the given scenario, the main memory is, let's say, 64 byte, the block size is 4 byte. So you can say 16 blocks will be created. The total number of 16 blocks. Let's say 1, 2, 3. So there are other also. Let's say I assume there will be more blocks like this created in the main memory. I'm just putting here. So these are the 16 blocks, right? Now, if this block be number, block number will be like 0, 1, 2, 3, 4 till 15. But because we are having 16 blocks, the block number should have 4-bit length. So I'm saying the very first block is numbered as 0000, and then 0001, 0010, 0011, 0100, 0101, 0110, 0111, then 1000, 1001, 1010, 1011, then 1100, 1101, 1110, right? So these are your block numbers. Order, let me write in the same order. So these are the block numbers from 0 to 15. So this is representing 0 number block, and this is representing 15 number block, right? Each block is having 4 bytes or 4 words. So let's divide this thing. I'm representing this, let's say like this. Considering this, so 4 words like this we are having here. And this side also, let's say 4 words like this. So these words are, I'm going to number, let's say this is word number 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So like this till 63, these are the word numbers. Each block is containing 4 words. So this main memory, I'm assuming, let's say it is having total 64 words. So as I have taken 1 word is equal to 1 byte, that means the main memory size is of 64 bytes, like this. Cache memory is having, there are certain number of lines. So let's say if cache memory is of 16 byte, total number of lines in cache, you calculate, you divide the cache size with block size or line size. So the size of cache is 16 byte, the block size is 4 byte. That means total number of 4 lines will be here. So as I have already created 4 lines, and these lines will have the capacity equal to the capacity of word, or equal to the capacity of block. Right. Now why this scheme we consider as direct map scheme? Because the mapping of the block with the cache memory is fixed. That mapping we cannot change. So in case one block is containing 4 words and the main memory is containing 64 words, if we calculate the physical address, writing physical address, or I'm saying PA, physical address is because we need to address total 64 words, and we do know that 64 different addresses we can generate by utilizing 6 bits. So physical address will contain 6 bits, right? Because there are 64 different words we need to generate address for, then we are going to require 6 bits. So the size of physical address in terms number of bits will be 6. Now, because one block is containing 4 words, the block offset, if we calculate, because we need to identify the stored words inside the block also. If we talk about the block offset, similar we have page offset and page offset. You can recall, I guess. So block offset, because there are 4 words, the block offset will be of 2 bits. So there will be 2 bits required to represent the block offset. And total size of physical addresses of 6 bits. Now these blocks we will be loading in line numbers, and there are total 4 lines according to the given data. So if there are 4 lines, the number of blocks or number of bits required to represent a line number, if we write line number, will be represented, because there are 4 lines, it will require 2 bits, right? So 2 bits will be required to represent the line number, 2 bits will be required as block offset, and the physical address is having, let's say, total 6 bits. So the physical address will be divided into different portions like this. So let's say physical address of 6 bits are there. There are 6 bits. The 2 bits are representing here block offset. I'm saying this is offset. The next 2 bits will be representing the line number, and the remaining bits, in this case there are 2 bits remaining, because this is 2 bits and 2, the total bits are 6. So that means these bits are 2 bits only, that will represent the tag. And what is the tag? Tag, every line will have one tag. So whenever we require some data, the tag bits will be compared, and then after comparison of the tag bits in direct map cache, it can be decided whether the data is available inside the cache. Now let's look at how this mapping is being done. In direct map cache, let's say there are 4 different lines are there, and we are using 2 bits combination to represent the line. So if this is line number 0, this is line number 1, let's say, the bit sequence of line number will be represented like 0, 0, 0, 1, 1, 0, 1. Now if we want to load the block which is having, let's say, number 0, we look at the least significant bit side, there are 2 bits, and we compare with the line number. So line number, let's say, is having 0, 0, and this is mapping with this. That means block 0 will be loaded whenever it need to be loaded in cache memory. It will always be loaded in line number 0. Similarly, this block number is also having the same 2 bits from the least significant bit side, which is mapping with the line number 0. Similarly, this is block number 0 and this is block number 4. This is block number 8 and similarly this is block number 12, right? So all these 4 blocks 0, 4, 8, 12, they will always be mapped with line number 0. So whenever they need to be loaded inside the cache memory, they will be loaded in line number 0 only. Now let's say if block number 1 need to be loaded, it will always be loaded in line number 1 because these bits are matching. Similarly, when line number 5 or block number 5 is need to be loaded, it will always be loaded in line number 1. Similarly, if block number 9 need to be loaded, it will be loaded in line number 1. Similarly, line number 13 will be loaded in line number 1. So I hope now you understand. If we need to load block number 2 or block number 6 or block number 10 or block number 14, they will always be loaded in line number 2. Similarly, if we want to load, let's say block number 3 or block number 7, block number 11 and block number 15, then these blocks will be loaded always in block number line number 3. So this mapping is fixed, it is not flexible in nature. That's why we consider this cache memory management scheme as direct map. Writing here direct map cache. Means mapping is directly given. Block number 0, 4, 8, 12 are mapped with line number 0. Block number 1, 5, 9, 13 mapped with line number 1 and so on. So that's why this scheme is direct map, right? So in this given scenario, we try to find out that how many bits will be required to represent offset. The offset length is dependent on the size of block in terms of words. So if your block size is of 4 words, that means your block offset will be 2 to the power 2, means 2 bits will be required. If your block size is of, let's say, 8 words, then block offset will require 3 bits. If your block size is of 16 words, then your block offset will require 4 bits and so on. So it is very easy to calculate the block offset. Then the line number bits will be dependent on the number of lines. So first you need to calculate the total number of lines by dividing cache memory by block size or line size. You will find out the total number of lines. And once you calculate the log base 2 of total number of lines, you will find out the number of bits required to represent the line number, right? So once you got the block offset bits and line number bits, the remaining bits will be tag bits. So in that way, easily we can calculate the tag bits and direct map cache memory management, right? I hope you are able to understand this. In this memory management, there is an issue. Let's say, consider a scenario that line number 0 is busy and let's say block number 0 is loaded here, or maybe block number is, let's say, 4 is loaded. So if block number 4 is already loaded here, saying BLK4, it is loaded in line number 0. Now anyhow the request comes for block number 8 and we need to load block number 8. In direct map there is no such flexibility that we can load the block number 8 anywhere. It is bounded that it has to be loaded in line number 0 only. Although line number 1 or 2 or 3 are available, they are free, nothing is loaded there, but in direct map there is no such flexibility. This block number 8 must be loaded in line number 0. So because of this, in direct mapped cache there are chances that the miss ratio of cache will increase. Miss ratio is whenever a block is being searched inside the cache memory and that block is not there, it increases the miss ratio. The total number of requests and the total miss, if you consider the ratio, you consider the miss ratio of that, right? So this is direct mapped cache memory management. In this scheme the mapping is fixed, so this scheme works in a faster manner. The text size is not comparatively large, it is small because line number is fixed, so we just need to compare the tag bit whenever the address comes. Compare the tag bits with the appropriate line number and we got to know that whether that block is available, the block or not. So let's say take a scenario and then we will wrap up this lecture. So let's say in this scenario one address is coming. So because this tag bit, these tag bits are of 2, there are 4 possibilities. So I assume that the tag bits here are, let's say I am assuming this is 1 0. There are only 4 possibilities. What can be the tag value? It can be 0 0, 0 1, 1 0 1. I assume that, let's say tag value is 1 0 is there, right? And let's say I want to check whether, let's say 16, I am requesting block number 16. So for the block number 16, if CPU is requesting it, the address will be generated in 6 bits. So the address, so rather than block 16, I am considering, let's say it is word number 16. So if you represent 16 word number, that is loaded here somewhere, right? It is somewhere here, it is in the block number 4, right? So if address is generated for word 16, I'm writing a word, the address in 6 bits will be 0, 16 means 1 0 0 0 0, right? So it is 2 to the power 0 1 2 3 4, 2 to the power 4 will give you 16. So this is the physical address which is being generated. Now once this physical address will come, we try to find out actually which block will contain this particular word which is being requested. So in order to find out the block number, we divide this physical address into 2 portions. So we know that 2 bits are representing block offset, and apart from the block offset, the remaining bits will represent the block number. So that means if we look at this representation, it is 0 1 0 0. 0 1 0 0 means If base 2, if we convert in decimal, that means it is 4. So that means fourth block will contain this word which is being requested. And because it is fourth block and the least significant 2 bits are 0, 0, that means this block must be mapped with line number 0. Now if it is mapped with line number 0, we need to map these 2 bits as a tag bits. So because here when we compare this 0, 1 with tag with 1, 0 and the tag is not being matched, that means it will be concluded this word which is being requested, or you can say word number 16, is not available in the cache because the tag is set as 10. I hope you are getting. So if the tag value is available right like 0, 1, and if the request comes for block number 16, if you compare, then immediately you will get to know that after comparing tag with the help of comparator, it will be claimed that there is a cache hit. The block is available inside the cache, right? So it will be more clear when we solve few questions on this scheme. For this lecture, it is sufficient, so I am closing this. Thank you everyone for coming.